Captions in English, please. So this is the first video on chapter 12, and it will focus on chemical bonding. So in 1988, researchers discovered the structure of HIV protease, a protein synthesized by the human immunodeficiency virus, HIV virus, which causes AIDS. So the virus HIV is synthesizing this HIV protease. It's necessary for it to replicate and multiply. Researchers used bonding theories. Bonding theories are models that predict how atoms bond together and form molecules. And so they used the bonding theories to simulate how potential drug molecules would interact with the HIV protease molecule. And so here you have a representation of the HIV protease. It's the gold colored structure in the picture here. And then the molecule shown in the center is indinavir, a protease inhibitor. So inhibitor means it by binding to the HIV protease, indinavir is not allowing the HIV protease to work normally. And so without HIV protease, HIV could not spread in the human body because the virus could not copy itself and AIDS would not develop. So that was the idea on how to stop the disease. With knowledge of the HIV protease structure, drug companies designed a molecule that would disable protease by sticking to the working part of the molecule. This is called the active site. So, biological molecules have usually active sites where other molecules bind to them, and that's how they, do their work. And so this, the drug companies try to find a molecule that would occupy the active site and not allow the HIV protease to work normally. And so by the early 1990s, these companies had developed several drug molecules that inhibit the action of HIV protease. And so we call these protease inhibitors. And so indinavir is one of them. And so in human trials, protease inhibitors in combination with other drugs have decreased the viral count in HIV-infected individuals to undetectable levels. So it seems to work. And although these drugs do not cure AIDS, so it does not get rid of the disease, it only stops from spreading it. So HIV-infected individuals who regularly take their medication can expect nearly normal lifespans. So they need to have access to that drug though. So to be able to inhibit, the HIV protease from virus in the human host, researchers have used bonding theories. And so what are bonding theories? Bonding theories predict how atoms bond together to form compound. So it helps to predict which compound will form and which compound will not form. So which combinations of atoms work and which ones do not work. Bonding theories predict why salt is NaCl and not NaCl2, and why water is H2O and not H3O. Bonding theories explain the shapes of molecules. So the shape here we refer to the structure, the 3D structure, which in turn determine many of their physical and chemical properties. Indeed, the structure of the proteins usually determine their physical and chemical properties. So what is a chemical bond? A chemical bond is a force that holds two or more atoms together and make them function as a unit. So there are two types of chemical bonds. The ionic bonds. So an ionic bond is formed by the attraction of a cation with an anion. that generally involve transfer of one or more electrons from a metal to one or more non-metals. So it's very specific, and this is something you will need to remember. Ionic bonds are formed from the transfer of electrons from the metal to the non-metals. And then the other type of chemical bonds are covalent bonds. The covalent bonds involves the sharing of electrons between two or more non-metals. So words are in capitals and bold because they are important. Here, covalent bonds involves the sharing, so there is no transfer there. Electrons are shared between two or more non-metals, so non-metals only. Again, you need to remember this. So let's look at a YouTube video here on bonding.
The periodic table lists all the substances in the universe that have only one type of atom in their makeup. Countless millions of other substances are made from combinations of these atoms. When atoms come together, they form bonds, and the resulting molecule or compound has a whole new set of chemical and physical properties. So let's look at chemical bonding and start with the most abundant atom in the universe, hydrogen. The element hydrogen has one proton and one electron, making it quite simple. The proton is positively charged in the center of the atom, and the electron is negatively charged and occupies a larger space outside the nucleus in the form of an electron cloud. This electron cloud surrounding hydrogen is often called an orbital. It is basically all the places where an electron has a chance to be found. Now let's bring another hydrogen atom into the picture. As we slowly start moving them closer to one another, we will show their combined energy on this graph. For a while, nothing changes. And then as they get close enough together, their energy starts to drop and eventually hits a minimum. And this makes the combination stable. This minimum energy distance between them is called a bond distance. And they are now sharing electrons. This is called a covalent bond. And instead of having two individual hydrogen atoms, we now have an H2 molecule. Moving the atoms any closer increases the energy greatly, since the positive protons in each of the atoms are repelling one another strongly. Covalent bonds come in different lengths and strengths depending on the atoms involved. These bonds are often shown as posts, lines, or dots between atoms. But of course, these are simply representations of places where electrons spend their time between atoms. In a covalent bond, electrons are shared, but they aren't necessarily shared equally. Let's take one of the hydrogen atoms and replace it with a fluorine atom. Watch what happens to the electrons throughout the atom. Fluorine, by its very nature, has a stronger pull on electrons in this molecule than does hydrogen. Fluorine shares electrons, but not equally. Instead, it pulls electrons closer to itself than to hydrogen. This is called a polar covalent bond. Each element in the periodic table has a tendency to pull electrons towards itself in a bond. This property is called electronegativity. When you alter the periodic table to show electronegativity, it looks a little different. Notice that elements on the left-hand side of the table, metals, have very low electronegativity values. They don't pull electrons towards themselves at all. As a matter of fact, they willingly give them up entirely. Table salt, as we know, is made up of sodium and chlorine, and so it is called sodium chloride. In forming table salt, the sodium atom gives up an electron and becomes positively charged. The chlorine atom picks up the electron since it is more electronegative and becomes more negatively charged. Now a very old saying takes over: opposites attract. So here, the atoms are drawn towards one another by their positive and negative charges. If there are enough atoms, we can eventually wind up with something as big as a single salt grain. This kind of bond is called an ionic bond. It is a very strong attraction between positive and negative ions. Most people differentiate this from a covalent bond by saying that in ionic bonds, electrons are exchanged instead of shared. Ionic bonds are very strong, stronger than covalent bonds. And you can easily see this difference. Melting sugar, which is breaking a covalent bond, is simple and makes caramel. Melting table salt is very different and requires temperatures higher than 1400 degrees Fahrenheit. Ionic bonds are very stable bonds. Very important, and much weaker than ionic or covalent, is a hydrogen bond. When hydrogen atoms connect to a small, strongly electronegative atom like fluorine, oxygen, or nitrogen, the resulting molecule pulls the electrons so strongly to the larger atom that the hydrogen nucleus, its one proton, is essentially exposed on one side. So it will bond to the negative side of any similar polar molecules. This bond is called hydrogen bond. The difference in strength of the different types of bonds is fundamental to allowing the DNA molecule to replicate itself. The bonds that hold the opposite sides of the double helix together, the A's and the C's and the G's and the T's, are hydrogen bonds and are very weak compared to the bonds that hold each letter to the backbone and the bonds that hold the backbone together. This allows the molecule to unzip easily, to expose one side as a template for replication. Life is all about bonds. Bonds, chemical bonds. Who knew?